BC excuse me, BC Calculus students, there we are. It's time to do some calculus. I'm doing section 5.3 of the book. And there's a really good explanation in there in the very beginning. I encourage you to read it before looking at this lesson. It'll make more sense if you read what they have to say here. This section right here. I would recommend you read this, page 285. They go through some explanations, and then they have a bunch of rules here that we're going to use to make sense of this lesson. I may have written it backwards on the Google sheet that I was, or the Google document that I was creating, but I do recommend that you at least look at that to get a sense for what's going on there. Okay, so this is called definite integrals and antiderivatives. The notes section, and then you'll have homework out of the book. And you'll do a Google document as well. So today we're going to focus on the rules of integrals. On page 285, I just showed you table 5.3 has a nice summary of those rules. And so the basic idea is that when you find the area under a curve using calculus, like this one, areas that are above the x-axis are positive. So this would count as a positive area because it's above the x-axis. And this would be a negative area because it's below the x-axis. That's just how integrals work, okay? And then if you integrate with a combination of areas above and below the x-axis, the areas above add to the overall area and the areas below subtract from the overall area. Okay, and then they talk about this in there. If you switch these bounds, the upper and lower bounds of an integral, upper and lower boundaries, the value of the integral becomes the opposite, okay? So if you integrate a function from a to b, it is the exact opposite as if you integrate from B to A, okay? And I think the easiest way of explaining that is just to imagine, you know, you're integrating some function, you know, on a curve, and you want to find the area from A to B, okay? And let's say you're just going to use a single Riemann sum. I'm sorry, a single rectangle for the Riemann sum, just one big old rectangle, okay? This would be, you know, the height would be evaluated at some particular value, okay? But then you would multiply that by the width. And in this case, the width would be b minus a, which would be a positive number. So you'd have a positive times a positive, which is a positive number. But what if you switched it and instead integrated in the opposite direction, right? You went from b to a. So the problem there is that you could still go ahead and evaluate that function here. But if you switch these and call this B and this A, you're now going to be doing, you know, f of A or f of B, doesn't really matter, whichever you choose, f of A, let's say you evaluated here, but now you're doing A minus B. And if you think about that, in the original setup, A is smaller than B. So when you do A minus B, you end up with a negative number. So that's kind of the simplest way I can think of to explain why this thing would flip around backwards. So anyway, this is a pretty basic rule. It may seem weird in the beginning, but you'll get so used to it. You won't, in a month, you won't even think about it anymore. You'll just know that that just flips it. Okay, so we have this curve that I made up. And what it's trying to say is the absolute value of this area is 7 square units. The absolute value of this is 8 square units. So I didn't put a negative there. I'm just saying that area, if you did that in geometry, would be 8 square units. And you understand in the context of an integral, that will probably be considered a negative area. Okay. This is 10, this is 12, this is 9, this is 20. Okay. And so you're going to get asked questions like this to evaluate the integral from, say, 0 to 5. Well, if I go from 0 to 5 in this direction, this is above, and so that would simply be 7 units because it's above the x-axis. Okay, if I go from 5 to 11, if I go this way, from 5 to 11, I'm going in increasing values of x. These are all underneath, and so that would equal -8, like so. It's underneath the x-axis. Okay, and then it says evaluate from 0 to 11, okay? And so one way of looking at this, and you're going to be expected to do this, is when you integrate from 0 to 11, you can actually break that down into 2 parts. You could first go from 0 to 5, and then you can add that to the integral from 5 to 11. And this is how they typically do things in textbooks. So we're going to evaluate this integral across 2 different intervals, okay? And so this is equivalent to breaking it into 2 pieces. And since we've already taken the trouble to figure out that this is 7, and we've already taken the trouble to figure out that this is -8, then we simply do 7 plus -8 or -1. Now, I'll be honest with you. Most students, when they get comfortable with this, simply look at this and go, well, you're going from 0 to 11 plus 7 minus 8, and there's your answer. okay? But you should be comfortable and familiar with breaking things down in this manner, because that's how the test will expect you to recognize it, and that's how the text will expect you to handle things, okay? All right, this case, I'm integrating from 11 to 17, so this would simply be 10 square units. Now, this time I'm going backwards, okay? I'm going from 24 to 17, okay? And so this is the opposite of the integral from 17 to 24 of f of x dx, okay? So the integral from 17 to 24 would be negative, and so this would be the opposite of a negative 12, which is just positive 12, okay? And so that's kind of a funny one, feels a little weird. You know, you're integrating from 24 to 24 to 17, and since it's below the x-axis, you switch the sign to its opposite. So then you consider it a positive area, okay? And that's a little weird. Okay, evaluate from 11 to 24, f of x dx. So if I go from 11 to 24, what most students do is they just go, well, you're going up. X is going up. It's increasing. So I'm going from 11 to 24. So this would be 10 and then minus 12 or negative 2, like so, okay? But you should be comfortable and in another way of analyzing this, you integrate from 11 to 17 f of x dx, and then you add the integral, picking back up at 17 and going to 24 of f of x dx. This is a whole lot more writing, but that way you can justify why it would equal this. From 11 to 17 is 10 plus, and then the integral from 70 to 24 is negative 12, and that gives you an answer of negative 2. So either way is fine. Okay, determine one possible value of a if the integral from a to 40 is negative 11. So that's interesting. We want to integrate to end up at 40. If I choose a as 29, I'd have an area of negative 20, and I need negative 11. So that's not going to work. Well, what if I start at 24 and go to 40? Then I would have positive 9 minus 20, which would do the trick for me. Okay, so what I'm going to do is I'm going to say that a equals 24. And so then if I integrate from 24 to 29, okay, so if I go from 24 to 29 first, and then I add up the integral starting at 29 and finishing on at 40, okay, of this function times its width, the function height times the width. The integral from 24 to 29 is 9, and the integral from 29 to 40 is negative 20 since it's underneath. So that would be 9 plus negative 20 or negative 11. So that's one possibility. A could be 24. Okay, the next one says determine a possible value of b if I integrate from 5 to b, I end up with an area of negative 1. So starting at 5, can I do this? If I do 8, if I start at 5 and I go to 11, that would be negative 8, and then plus 10, and then minus 12, and then plus 9. So let's just see if I can figure this out. If I start at 5, I'd have a negative 8 first, and then I would add 10, and now I'm at 2, and then I would subtract 12, and now I'm at negative 10, and then I would add 9, and now I'm at negative 1, okay? And so what I'm going to do is, to get to here, I'm going to have to integrate to 29. So what I'm saying is the integral from 5 to 29 of f of x dx is equal to, so it would be, just like I said earlier, starting at 5, it would be negative 8 plus 10 minus 12 plus 9, like so. And if I do that, I end up with, let's just double check, negative 8 plus 10 minus 12 plus 9, sure enough, equals negative 1. And so, you guys, it's very important you answer the question. This is not the question it asked you. It said a possible value of b, and so we need to be very clear that b is equal to 29, like so, okay? All righty. Marcy says that when she did problem G, she chose a value of a about halfway between 29 and 40. So she chose some value in here of a. she said, I'm going to put A there. Since the overall area would be negative 20, it's underneath, integrating about half of it would produce an area of about negative 11. Is Marcy's reasoning sound? Okay. Well, we don't know the specific function here. To be honest, I just drew it in Microsoft Word, so it probably is. You could probably calculate it what it is based on all these other points I gave it. But her idea here is if you start A here, you'd have negative 20. If you put A here, you'd have like negative 1 or 2. If you put A at 40, you get 0. So her argument is somewhere in here there has to be an intermediate value where it would in fact work. And this honestly is an application of the intermediate value theorem. We know if we put A here, we'd have negative 20. We know that this integral is continuous. This is a differentiable function. And so there has to be some value of A in here where we'd have just the right amount of area of negative 11. There has to be some, there must be, by the IVT, she is correct. By the IVT, the intermediate value theorem, there must be such a value. Now, we don't know it. The beauty of the intermediate value theorem is it doesn't tell you how to find it. It just says there must be one, okay? There must be such a value since the integral from 29 to 40 of f of x dx is equal to negative 20. And the integral from 40 to 40, if you don't move anywhere, if you don't move at all, that would be 0, right? And negative 11 is between those two. So negative 11 is in between these two possible values. The integral from 40 to 40 of f of x dx. Oops, I forgot the dx there. And negative 20. So the integral from 29 to 40 f of x dx. Okay, so this is a fancy way of basically saying, yeah, Marcy's got it by the intermediate value theorem. Okay, all right, next problem. This is a very common theme. You're going to be expected to use the average value of a function. We're going to put this in our Wubby soon. Okay, and you can memorize the formula, and then you get all, tongue-tied and twisted and forget it on the day of a test. So I don't recommend that your sole way of managing this course is pure memorization of everything, though you guys are generally much better at memorization than I am. I recommend you understand the underlying concept. So one application of integration is that it may help us determine the average value of a function over an interval. So the average value of a function would be like waking up in the morning and every hour writing down the temperature. Okay, and you'd have 24 different measurements, and you'd take the average of those 24 measurements. So if you have a graph of the temperature changing during the day, you would have the average value during the day. And oddly, they never publish that really for weather. They always give the high and the low, and they really don't do the average, which is kind of interesting to me. Perhaps knowing the average temperature during the day isn't very helpful, especially in Colorado. You guys know that the temperature can swing from 48 to 87 on the same day, so maybe the average isn't terribly helpful. Okay, in any case, one application of integration is that it may help us to determine the average value of a function over a closed interval from A to B. And to be honest, it could be an open interval from A to B, as long as you don't have crazy things going on at the endpoints. Think in terms of a rectangle having the same area and width as the original integral. And so what we're trying to do is we're trying to make this shaded area equal that area. And we want this width, this to be the same. That's always going to be b minus a in both cases. Okay, so this integral here represents that gray area there. If we integrate this, we have this area here. And what I want to do is I want this area to equal that area. Okay, so I want the area of the integral to equal the area of the rectangle. Okay, that's all I'm trying to do is set those two things equal. Okay, well, what do I call the height of this rectangle? Well, that height right there is exactly the average value of the function. Okay, in order for this to work, that height there has to be the average value of this function over here. Okay, and I actually went ahead and calculated it to draw it in there. So what I'm trying to do is draw this line on here just right so that that gray area above the dotted line, that little tiny piece there, you throw that in here, you throw that in here, that would equal out. Okay, so if you imagine having, like a piece of paper and you literally cut this out and you cut this piece out and you start to stick it in here, the amount of gray area above would exactly match the deficit right here. That area would fit right in there. And so that's the average value of the function. So then it's just a question of solving for this variable here, the average value of the function. Okay, so the area represented on this side is just by definition the integral from a to b of f of x dx. That's what this area is. And that is equal to the area of a rectangle. Its base, b minus a, times its height, which is the average value of the function. Okay, so there you go. Okay, that's real. You're just equating those two areas. The area under the integral is exactly equal to the area of this rectangle. And by definition, this height here has to equal the average value of the function. Otherwise, this whole thing falls apart. Okay, I'm going to catch you at the next video just in case I have shaky video today, okay? Catch you at the next video. All right? Bye-bye.